So section 8 deals with inverse functions. We're going to introduce the topic using a lot of linear functions, but in the long run, the most important inverse functions involve trig functions and the relationship between logarithms and exponentials. So you'll see this again. If you take calculus, you'll see this again. And I'll assume that you know what's going on here. Okay, so we have 13. So the next, how many problems? About 6, I think. Ask you to find the inverse functions algebraically and to show them graphically. Okay. So I think what we're going to do, we're going to just pause for 1 second and get things set up here. Okay, so what I've done is just set up my graphing program so I can graph these things. Okay, so, actually, it says the first couple just say to show whether they are inverse functions. I was thinking you had to find the inverse function, but so there's two. Algebraically, what you do is you do f of g of x and g of f of x, and then if they're inverse functions, then the answer should be x. So f of g of x, you take your f of x function and you plug in your g of x function, and then you simplify, and you see you get x, so that's good. And then if you do g of f of x, there I would take my base function, which is x over 2, and instead of x, I would put in 2x. So again, you can see that simplifies down to x. So that proves algebraically that they're inverse functions. And if I plot those two functions, so if I plot f of x and g of x, and I graph them, what you'll see is, and I'll also plot the line y equals x. And what you see is that they're symmetric around the line y equals x. So and this is a little confusing because of the scale. So let me see if I can change the scale a little bit. What I'm trying to do is make these squares, these be squares here. So I think what I have to do is zoom out in this direction. So that's pretty square. So now you can see this is a diagonal line, and you can see that they're symmetric around that. Okay. The next one, 15. So f of x equals 7x plus 1. G of x equals x minus 1 over 7. Okay, so again, algebraically, we do the composite function. So we get 7 times x minus 1 over 7 plus 1. 7's cancel out. That gives you x minus 1 plus 1, which is x. So that's what we're looking for. G of f of x. So there, what we do is we're going to plug in 7x plus 1 for x. Then we subtract 1, and then we divide the whole thing by 7. So if we take the parentheses away and we cancel out the 1's, because there's a plus 1 and there's a minus 1, you end up with that, and the 7's become 7 over 7 is 1, so you get x. So that shows that algebraically that they are inverse functions. Now we'll do the same thing here. So we have 7x plus 1 and x minus 1 divided by 7. Plot those. Something's wrong. No, they're right. Okay, so you see they meet right here on the green line, and then they are equal distant from the green line. The red line and the blue line are equally distant on opposite sides, so that proves that they are inverse functions. Okay, 17. F of x equals x cubed over 8. G of x equals the cube root of 8x. Our composite function f of g of x is equal to, so we're going to plug that into here, so we get the cube root of 8x, whole thing cubed, divided by 8. So instead of x, I plug in g of x. Well, the cube root cubed is just the argument, so you get 8x for that. For the numerator, you get 8 in the denominator, which cancels out and becomes 1, gives you x, so that's good. And g of f of x, there what we do is we've got the cube root of 8 times, instead of x, we multiply by x cubed divided by 8. So the 8's cancel out, become 1. So you've got the cube root of x cubed, which is just x. Okay. So now we'll plot them. So f of x is x cubed divided by 8. G of x is the cube root, and the way you do that is x to the, actually I got a cube root of 8x. So you take 8x raised to the 1/3 power. That's how you make a cube root using fractional exponents. And I plot y equals x, and I get that. This is invalid comma. Oh, I think I have to use a semicolon between those. Okay, so there it is. So again, the blue and the red curves are symmetric about the green curve. You can see that any intersections are right on the green line. That's kind of cute. Okay, moving on. 19. We got left 3. Okay, so 19, f of x equals the square root of x minus 4. G of x equals x squared plus 4 with x greater than or equal to 0. And that's so that this will be defined. If x was less than 0, then this function wouldn't work. So again, we do our composite function. So we have the square root of, instead of x, we put in g of x, x squared plus 4 minus 4. Notice the 4's cancel out. 4 minus 4 is 0, so you get the square root of x squared. Square root of x squared is x. G of x, g of f of x. Okay, so we plug that into here. So we get the square root of x minus 4, the whole thing squared, plus 4. And so when you square root, you just get the number, the argument. So we get x minus 4, and then we add 4, which is x. So that's analytically proven to be true. And then we plug that function, those two functions in. So what do we have? We have square root of x minus 4 and x squared plus 4. And we're only going to look at x greater than 0, so ignore what we get below there. So we don't look at that part. So this part and this part are symmetric around the line, the green line here. And we, like I said, this stuff And that's because there is no red curve on this side, but there is a blue curve. Okay, 21. F of x is equal to 9 minus x squared, where x is greater than or equal to 0. And the second one is g of x equals square root of 9 minus x. Now, we probably, well, we're going to let x be greater than 0. You could actually have this defined, let's see, just thinking about this. If x is actually, oh yeah, there is some additional, like there's got to be something else on this thing. So here x has to be less than or equal to 9, because when x is greater than 9, this becomes negative, and we can't take the square root of a negative number. So we can only look at these two functions having inverses between 0 and 9 because of the limitations on the domains of each one. Now we don't see that when we do the composite function. So if you take 9 minus the square root of 9 minus x squared, so I'm plugging that in for x, you'll get 9 minus the quantity 9 minus x, and you see the 9's cancel out, and then the negative times the negative is a positive. So that works out analytically, and g of f of x is, we plug that into here, so you get the square root of 9 minus x, but instead of x we put in 9 minus x squared, and so you'll see again the 9's cancel out, and then you get negative times the negative, so you just end up with x squared, and you take the square root of x squared and you get x. So it's true in that sense. Now when we go to the graph, what we'll do is we'll show it for larger values of x, but we'll see why it doesn't make sense for that. So one function was 9 minus x squared, which is actually good for all real numbers. Anyway, let's look at why we have to limit that. And the second one was the square root of 9 minus x. Yeah, so that looks a little crazy. So what we're saying is from 0 to 9 that the two functions are inverses of each other. So what I'm going to do is I'm going to change the values on x. So it goes from 0 to 9, and I'm going to have y go from, let's see, from negative 10 to positive 10. See what that looks like. Okay, so the question is this symmetric around the x-axis? And the problem is this thing is not, it's not square. So let me see if I can make this thing a little square. And let me make sure the functions are right, because these are both on the same side, so something doesn't look quite right. So we have 9 minus x squared, square root of 9 minus x. And, okay, so that seems to be okay. So what's going on here? Actually, these things are not square yet. Let's see. I'm going to pause for just a second. Think about this. Okay, so I've got the scale right now. So this point way up here corresponds to that point, and this point corresponds to that point, and they cross right there. So, and you can see it's about a square. It's about 1 by 1 square that looks square. So that in that scaling, it looks like an inverse function. So that was the problem. Okay, so that's 21, 23. So you got f of x equals x minus 1 over x plus 5. G of x equals negative 5x plus 1 divided by x minus 1. So that looks interesting. So what we would do is, again, we're going to do f of g of x. So for x, we plug in g of x. It's going to be so exciting. Okay, 5x plus 1 divided by x minus 1 minus 1 divided by, make sure I'm doing the right function here. Okay, yep. And so this negative applies to both terms in the numerator. Then in the denominator you have, for x, we put in negative 5x plus 1 over x minus 1 plus 5. Okay, so let's see what we're going to do here. If we get a common denominator here, so this term, negative 1, would become negative x minus 1 over x minus 1. So when you add those two together, you're going to have a denominator of x minus 1. And I'm going to apply this negative to those two terms. So you have negative 5x minus 1 here, and then you're going to have a negative applied to that. So you're going to have negative x minus plus 1. So this negative makes this negative, makes that positive. And you can do the same thing in the denominator. So we're going to have x minus 1 as the common denominator. And then you'll have negative 5x minus 1, and then you'll have 5 times this number. So it's going to be minus 5x plus 5. Okay, let's see if this is working out. So now these two cancel. And then you can combine these terms. So you get negative 5x minus x. So that's negative 6x. You get minus 1 plus 1, which is 0. Down here you get negative 5x. Oh, wait a second. We've got a problem here. So this actually here is going to be, so it's 5 times this, but it's positive, so it's going to be plus 5x minus 5. So you take 5 times this, you get 5x minus 5. So these cancel out here, so you end up with negative 6 in the denominator, and that simplifies down to x, believe it or not. So it did work. And then you have g of f of x. So it's kind of the same thing, g of f of x. So we plug that in here. Oh, that's what I already did. We got to go the other way. So we're going to plug that into there. So you get negative the quantity instead of, so you'll have 5 times x, but x is x minus 1 over x plus 5. And then you add 1 to that. And then you divide by x. So for x, we put in x minus 1 over x plus 5, and we subtract 1 from that. So we're going to do the same kind of thing that we did here. If we apply the negative sign to both of these two terms, we're going to get negative 5x plus 5, and then divided by x plus 5 plus 1. So all I've done is take this negative 5 multiplied by that, negative 5 times that. And in the denominator, I'm okay. I can just leave it as it is right now. So we get that. Now again, I'm going to create a common denominator. So you're going to end up with negative 5x plus 5. We're going to have this all over x plus 5. So this is going to be x plus 5 over x plus 5. So I'm going to add x plus 5 to there. So this part is 1. This part is that. And then I'm going to divide by the whole thing. So you end up with x minus 1 here. The common denominator is x plus 5 again. So we take x plus 5 divided by x plus 5, like that. So this part is that, and this part is that. Well, these cancel out. Combine like terms, so you're going to have 5x plus 5 plus x plus 5. So what is that? That is negative 4x plus 10, and something is not working out here. Oh, because this was a negative 1. Okay, that's where it's messed up. So this is going to be, so there'll be negative 1. Let me fix that there. Erase that. Okay. So this one looks right, I think. Negative 5x. So let's try this again. Okay, so x, so you get, so what you're going to have is minus x minus 5. Because you get x plus 5 times negative 1. And then you divide by x plus 5. And these cancel out, and those cancel out. So we end up with a negative 6 in the denominator. And there must be a sign error somewhere here. So let's think about it. Let me just pause it. I found, because this should cancel out to negative 6x. And if this were negative and this were negative, that would work. So there's obviously there's a sign issue somewhere here. So let me, I think I know what it is. So this negative sign here applies to this whole thing. So this should be so you have the negative sign here. So what that means is this negative sign is here, and it's also here. So that's negative. So that should be negative. And when I multiply that out, those both should be negative. Negative x minus 5. So you can see those cancel out. And your negative 5x minus x is negative 6x. The negative 6x is cancel out. You get x. Okay. So we see that f of g of x, and g of f of x work out. And so now let's go back to our standard zoom, and we'll plot these things. So the first function is x minus 1 divided by x plus 5. And the second function is negative the quantity 5x plus 1 divided by x minus 1. Gotta put that in parentheses. And that looks right, so I graph it. And there it is. Beautiful. So again, where they intersect, they touch the green line. These are two symmetric things. I should make this a little bit, so I can make these things square. So there you go. Now you do have this one little part here, which I don't know if there's a corresponding thing, a blue part. Let me just zoom out. Oh yeah, okay, so there they are, all there. Okay, so that's the first part. The second part is probably calculating the inverse functions given the functions. So it says find the inverse function of f, then graph both the function and its inverse on the same set of coordinates. Okay. So 40 is 3x, f of x is 3x plus 1. So how do we find the inverse? Well, the first thing you do is you replace f of x with y, and then you solve for x. So if you subtract 1 from both sides like that, divide both sides by 3, you get that. Or x is equal to y minus 1. Now, at that point, you say this is the inverse function, and then you switch the variables. So we say, y equals x minus 1 over 3, and therefore g of x, the inverse function, or we could say the f prime, the inverse function, or x to the f to the minus 1, is equal to, put y in there, so we get y minus 1 over 3. So this is actually that's not right. It's just as it is, because it has to be a function of x, not a function of y. So then what we do is we say the inverse function of the original function is x minus 1 over 3. So that's the original function here. And down here we have the inverse function. So now we're going to plot those two. So let's go to the graphing program. So let's go back to standard zoom. Put in our original function, which was 3x plus 1. The inverse function was x minus 1 over 3. X minus 1 all over 3. And plot y equals x. And there they go. And again, we'll change the zoom so that those little squares are square. So there we go, that's good. 42. So that's f of x equals x cubed plus 1. For f of x, you put in y. You solve for x, so you get y minus 1 is equal to x cubed, or x is equal to the cube root of y minus 1. You switch the variables, y is equal to the cube root of x minus 1. And then we don't have to do plus or minus here because it's an odd root. So then you say the inverse function is the cube root of x minus 1. So let's plot those two. So you've got x cubed plus 1. The inverse function is the cube root of x minus 1. So we take x minus 1, raise it to the 1/3 power, and we put in y equals x. we graph it. There you go. So that looks good. 44. So the original function is square root of x, which has a domain. X has to be greater than or equal to 0. And actually that's 43. Sorry. 44 is f of x equals x squared for x greater than or equal to 0. And this limit is because a function has to be one-on-one to have an inverse. So what you do is just take this part, not the other part, because this function is not one-to-one. But if you limit the domain to positive real numbers, then you're in good shape. Okay, so set f of x equal to y, solve for x is a function of y, so you get y equals plus or minus the square root of y, but we're just going to use the positive square root because that's the part that is it we're interested in. And then you switch it, so you say y equals positive the square root of x, and then you say the inverse function is just equal to the square root of x, and x has to be greater than or equal to 0. So now we'll plot those two functions. So the original function was x squared, the inverse function was the square root of x, and the comparative function is y equals x. And you graph those, and if we only look at values of x greater than 0, you can see that the two functions are inverses of each other. We just ignore that because that's not in our domain. (46) f of x equals x squared minus 2. X is greater than or less than or equal to 0. And the problem is if x is greater than 0, when you take the inverse of this thing, you're going to find out that at x greater than 0 that it's not going to work out. So let's just see what happens. So you say y equals x squared minus 2, add 2 to both sides, take the square root, so you get x is equal to the square root of y plus 2, and something's just doesn't seem right. Well, one thing you can see is that if x is greater than the square root of 2, well, it shouldn't. Let's just plot this thing out, see what it looks like, and try to understand why they're limiting the domain this way. So it's the function is x squared minus 2, and we're saying that the inverse function is, well, we got to switch the variables here. So you switch it, you get y equals the square root of x plus 2. Therefore, the inverse function is the square root of x plus 2. So let's plot that. Square root of x plus 2. Graph it. Okay. So I can see, here at for x, I mean, right here, the two functions are inverses of each other. They're symmetric around each other. But Something doesn't seem, over here it doesn't make any sense. And the original function was this one. Well, actually, these 2 points are still symmetric of each other. So this is the part right there. So it looks like for x less than 0, there is no inverse function. So maybe that's what they're trying to fake us out. So let's check the answer here, because at x greater than 0, it is. They are inverse functions. But for x less than 0, it looks like it doesn't have an inverse. So this is problem number 46. So let's see what it says. Is this really 46? Okay, maybe I made a mistake. So let's go back and look at what I did earlier. So this is plus or minus the square root. And I guess they're saying that we take the negative square root instead of the positive square root. So let's plot that instead. So that's the inverse. So let's go back to the graph. So what I do is I make this negative the square root, and I graph that. And so, okay, yeah. So what happens is, you have the blue function, and you have the red function. And for x less than 0, which is this area, this is the inverse of that. You ignore that part, and you ignore all the other stuff. So I guess it is true. You just have to use the negative square root instead of the positive square root. Interesting. That's a little fine point. 48 f of x equals negative 2 over x. So we say that's equal to y. So we get negative 2 over y. So if we multiply by 2 and divide by negative 1, we'll get, actually what I'm trying to do is solve for x. So let's switch x and y. So you get x is equal to negative 2 over y. And then we switch the variables. Y equals negative 2 over x. And you say f prime of x is negative 2 over x. Looks like the same function. So what does that mean? Well, let's just plot this function and see if for part of it it's an inverse of the other one. So I'm just going to plot negative 2 divided by x. Let's see what it looks like. Okay, so yeah, you kind of see that this side is the inverse of that side. I wonder how they explain that in the book. So let me just see what it says. So which one was that? That was 48. Okay, look at the right hand. Let's look at the odd ones. Let me look at the even ones. Okay, 48. So yeah, the inverse function is the original function. So that was right, even though again a little weird. And then 50, we have x minus 3 over x plus 2. So same procedure. Replace f of x with y. Then solve for x. So how the heck do we do that? So I'm going to multiply by, so if we take, just multiply that out, x, y times x plus 2 is x minus 3. And so we get yx plus 2y is equal to x minus 3. We put the two terms that involve x on the same side, so you get y times y, y times x minus x, and then we move this to the other side, so it becomes negative 2y minus 3. And then we factor out the x, so you get x times y minus 1 is equal to negative 2y minus 3. And then you divide both sides by the property, the term in the parentheses. So that's what I get. So now we're going to plot these. X minus 3 over x plus 2. X minus 3 divided by x plus 2. And the second function is negative 2y minus 3, negative 2y minus 3 divided by y minus 1. So actually I need to put in x's for that. I'll go back and fix that in a second. So it's x minus 1. Okay. So before we plot that, once you solve for x, then you switch the variables again. So you get y equals negative 2x minus 3 over x minus 1, and then you say f inverse function is equal to negative 2x minus 3 over x minus 1. So that's what we're plotting, and we do that, and there you see it's happening. So this reflects to here, that reflects to there. So it looks like it should.